want to talk now about polarization, which is a particular wave property of light, or at least a property that we can think of as being emergent from the fact that light is made of electromagnetic waves. So if we draw a picture of the electromagnetic wave here, we've got the electric field pointing vertically, magnetic field perpendicular to that horizontally, and the direction of propagation perpendicular to both of those along this axis. In this case, we would say this light is polarized vertically. So the polarization is the direction of the electric field vector. In this case, it's going up and down in the vertical direction, so we call that vertically polarized. If I were to rotate the electric and magnetic fields by 90 degrees around the axis of propagation, then we would have horizontally polarized light with the electric field pointing in the horizontal direction. So the axis of polarization, the direction of polarization, is the direction of the electric field. This example here is an example of linear polarization, where it's just in one spatial direction. There is also a kind of polarization which is circular. In this case, the direction of the polarization vector, the direction of the electric field vector, in other words, rotates as the wave propagates. So at this point in the propagation, the electric field is pointing horizontally. Over here it's pointing down, and over here the electric field vector is pointing up. As the wave propagates, the direction of the electric field rotates. And so the direction of the electric field does a sort of a spiral as the wave propagates. And the spiral could be in either direction, so we then have definitions of left and right circular polarization. In fact, we can have some combination between these two, where the direction of polarization can be, or the polarization can be described as elliptical, whereas instead of having a constant amplitude of the electric field as it rotates through space, the amplitude can change as this thing spirals, and that would be what we call elliptical polarization. But the polarization is, in this way of thinking about it, a property of the light that exists because it's a wave, and the direction of the electric field vector gives you the direction of the polarization. Now here's an application of polarization. We haven't done Snell's law yet formally in this course, and we will come to that, but I'm sure you're all familiar with what happens when light hits some change in dielectric constant. So we go from refractive index n1 to refractive index n2, and the direction of propagation changes as you cross this boundary. So if n2 is higher, this angle of refraction is a little lower than the angle of incidence. Something interesting happens to the polarization in this case as well. So the light coming in here we can imagine as being a mixture of different polarizations. We've got polarization in this direction, which we would be, well, let's call that vertical, and some polarization which is horizontal, so that's sticking in and out of the page here. And if the light comes in at the special angle called the Brewster angle, you can have a situation where all of the light reflected has only the polarization which is horizontal. That means all of the vertical polarization in this case is transmitted. Now, not all of the light that is transmitted is vertical, because some of the horizontal will be transmitted as well, but all of the reflected is purely horizontal. Now, a special property of the reflected and refracted waves in this case is that they are at right angles. And you can show that the Brewster angle is given by the arctan of the ratio of these refractive indices. Now, an example of what this can do, this is a photo of some water taken without a polarizing filter. If I put a polarizing filter on the front of the camera lens that blocks all of the horizontal polarization, then we no longer see a reflection from the surface of the water, and we can see what's under the water much better. So that would be blocking all of this horizontal polarization here, and at the Brewster angle, that is all of the reflected light. And so in that case, ideally we see no reflected light at all from the surface of the water. And in that case then, we don't see the reflection of the clouds as we do here.